So here we go again with the single electron atom. So we call this the hydrogen-like or hydrogenic system because these are all situations where the atom is a lot like hydrogen, and the simplest case is indeed hydrogen. So again, we've got a nucleus here with a charge plus Z. We're going to call it Pauli the proton, and then we've got some electron out here. There's only one of them, and its name is Clarissa. And the charge of Clarissa is -1 times the fundamental charge E. So the proton, in the simplest case, has a +1 charge. More generally, it has a plus charge equal to the number of protons in the nucleus, and we've got one single negatively charged electron. There's a distance between them. It's a radius. It's r. The problem has what we call spherical symmetry. And remember that Clarissa is about 2,000 times lighter than the proton and correspondingly lighter than the nucleus as the nucleus gets heavier and heavier and heavier. So this comes very, very close to having the electron in motion around a completely stationary nucleus. Technically, the whole system is revolving about the center of mass, but the center of mass is awfully close to the center of the nucleus. The nucleus barely moves, but it does technically move a little bit. The potential is a central force potential. It's equal to -z times 4 pi divided by 4 pi epsilon naught times the fundamental charge squared divided by the radius. So -z when we have a charge. But the key is that we have this central force potential that depends only on r. So the energy goes down to -infinity at r equals 0, and then we use 0 at infinite separation as the bounding limit because of that, and we can make kind of a 1 over r shape. So what we have is this kind of pinhole drain of very large negative energies due to the Coulombic attraction as the electron gets very, very close to the proton. But if you consider that as we can move the angle through both phi and theta through all their possible values, this is very much a confining potential. So this is trying to hold Clarissa very close to the proton, and it's going to suffer from all of the issues that a confining potential suffers from, in that the wave function is going to have to go to 0 as we get away toward high r, and as a consequence, because we have to normalize the wave function, we're going to have some kinetic energy because we're going to have some curvature in the wave function, but we're fighting against this approach to -infinity in the very depths of the potential. So that makes it kind of interesting. But in the end, we still have to solve the Schrodinger equation. So we have the Hamiltonian operating on a wave function, which is a function of radius, co-latitude, and azimuth. And that's going to equal to the total energy times the wave function. H psi equals E psi. It's always that. And in this case, it's -h bar squared over twice the mass times del squared, operating on psi, times a potential of only radius, multiplying psi, the wave function, equals the total energy times the wave function. And so we're going to postulate that the wave function is some function of r, which we're going to call big R of r, and then some function of the angles. And just because, we're going to call that function of the angles y. And that's kind of a leading assumption there, because we've already seen that guy. But we'll get there in a second. So the del squared operator, the second derivative operator, if you recall from Unit 2, is actually equal to this 1 over r squared d by dr of r squared d by dr plus 1 over r squared of the Legendrian. And if you actually separate, you plug all that stuff in and work through a bunch of manipulations, which you can find in the notes, you wind up with a separation that looks like this. You can pull all of the radial dependence over to the left-hand side. The potential kind of comes with that as well because it is dependent on the radius. And so the left-hand side of the equation has grabbed onto the E minus V, the kinetic energy term. It's got the total energy term in there. And then there's a right-hand side of the equation, which is all the angular stuff. And so as always with this separation of variable, I got a left-hand side that depends on radius, I got a right-hand side that depends on angle, and I'm allowed to choose any radius and any set of angles that I want. They've got to be equal to each other, and the only way that can be true is if they're equal to a number. each, because that's the only thing that will stay the same as I independently vary the independent variables. So that's good. Well, the right-hand side there, we've done that. Oh, I also should point out that the mass of the electron has now been switched to a reduced mass, but that's a technical detail that only spectroscopists care about. It's basically the mass of the electron. Okay, so we know the right-hand side. We already did it in Unit 2. The solution is YLM, which is why we used Y of theta and phi, and the principal, well, the total angular momentum quantum number L can be 0, 1, and it'll move along to something, and then poor old m sub z is confined to be between negative L and plus L. We already solved that problem. The total angular momentum is h bar times the square root of L times L plus 1. And the z component of angular momentum is h bar times m sub z. So you had better be familiar with those solutions at this point. So what we need to do is turn our attention to the left-hand side, and basically, without working it out, this turns out to be a total energy of minus the reduced mass times e to the fourth power times the nuclear number squared divided by 4 pi epsilon naught squared times 2h bar squared, and then we get a 1 divided by n squared dependence. So the energy levels go like 1 over n squared, and n is going to be the principal quantum number. N can be 1, 2, 3, etc. So the total energies are negative, and that's basically, if you look up at the potential again, if we get above 0 in total energy, we're not confined anymore. The electron is free and the system is ionized. So to be at any confined system is going to have a negative total energy. And it makes sense. We have the 1 over n to the, it turns out, second power, so the 1 over n squared dependence, because when n equals 1, that term is, well, 1. It's the largest negative number we can get, and it's fractions after that. So it's 1, 1/4, 1/9, etc. So the lowest, the quantum number, n equals 1, has the largest 1 over n squared term, which means it has the most negative energy. So it's the lowest energy solution, which it had awfully better be. So that thing all works out, all makes sense there. Now, the L, the other thing that happens here is the principal quantum number n has grabbed onto the energy solution, and it also places a constraint on the L quantum number. So now you notice over to the right there, L can go from 0 to n minus 1. And the explanation for this is the same as the explanation that we went through for the total angular momentum and the z component of the angular momentum, as indicated there by those two values. With the angular momentum, you can't have a larger z component of the angular momentum than you can have total angular momentum, and so quite clearly m sub z has to be no greater than the absolute value. The absolute value of m sub z has to be no greater than L. And the same sort of thing applies when we think about energy. There is energy associated with rotation. It goes like L squared, and it's L squared over 2I, in fact. And that energy can't be any more than the total energy. That kinetic energy can't be any more than the total kinetic energy. And so the n turns out to place that if you work it all through, that means that L has to be less than n. So the largest L is n minus 1. And the rest of the energy is going to be associated with radial motion, moving in and out, which this does quite a lot. But those motions, the angular and the radial motion, are now totally coupled to each other. And the total energy is not given, it doesn't depend in any way on that angular quantum number L, or m sub z. It only depends on the principal quantum number n. So the system has worked itself out. We've got 3 quantum numbers, n, L, m sub z, and they order themselves. So the principal quantum number takes on the total energy, L takes what's left, which is the angular part of the motion, and describes the total angular momentum, and then m sub z is the orientation or magnetic quantum number and describes the z component thereof. So that's how it goes. This is actually equal to minus h bar squared over 2 mu a naught squared times z squared, 1 over n squared. And that looks familiar. So the h bar squared over twice a mass times a distance squared looks a little bit like particle in the box type. Answers the prefactor in the first expression there over in the left is an awful mess. But this thing A naught that has popped up, we call that the Bohr radius. And A naught is 4 pi epsilon naught h bar squared over the reduced mass times E, the charge, squared. And that's known as the Bohr radius, and it's about half an angstrom. It's 0.529 angstroms. Notice it does depend on the reduced mass. All the other terms, pi, epsilon naught, h bar, and the fundamental charge, those are constants of nature, but there is a reduced mass hiding in there. And so sometimes, in fundamental physics at least, we have systems that are a little bit different than electrons, and even as z changes, that reduced mass does change subtly, and so there is a slight dependence there on the mass, but that is a very small value. So the mu we've quoted here, 0.529 angstroms, is the case where we're just using the mass of the electron. But that's a small, but to a spectroscopist, important detail there. Now, we got that set up. We can go one step farther. This thing is minus z squared times a thing called RH times 1 over n squared. That's a pretty easy expression. RH is a thing called the Rydberg constant for hydrogen. That's the sub h. And it's equal to 109,677 wave numbers. And it is the scale for this problem. So now we have 3 scales in our world. We have the scale of rotational energy, and remember that's 1 to 10 wave numbers, very small number. We have the scale of vibrational motion, and that is, as we just discussed in the previous video, that's of order 3,000 wave numbers. If we use hydrogen here as their base system, then rotation is maybe 15 wave numbers, vibration is maybe 3,000 wave numbers, and all of a sudden we've gone to 110,000 wave numbers for the electronic motion. Completely different, vastly larger energy scale for electronic transitions. I should also point out a 4th scale that we've used. Bonds, chemical bonds, a single sigma bond is of order 30,000 wave numbers. So really there are 4 scales. Rotation, 15 wave numbers. Hydrogen vibration, 3,000 wave numbers. Single bonds of order 30,000 wave numbers, and now the energy of a single electron near a hydrogen, 110,000 wave numbers. Those are critical numbers that you should remember.